I would like to prove the Pythagorean theorem as well as the inverse Pythagorean theorem using similar triangles today. The proof isn't too hard. There are many ways to prove the Pythagorean theorem, but I'm just gonna use similar triangles and then prove the inverse Pythagorean theorem as well, just in the same video. So here we have a normal right triangle right over here. Okay, it has the legs A and B and the hypotenuse of it being C. Okay, and then here there is this line segment right over here from this vertex, and it goes all the way down, and then it hits this line segment C. Okay, I guess you can say it's the altitude of this vertex right over here, because it goes down and then it meets this line segment at 90-degree angle. Okay, so with this construction we have similar triangles being made, because if you look at the larger triangle, we have it where angle phi plus angle theta, this gives me 90 degrees, right? Because the angles of a right triangle, of any triangle I should say, add up to 180 degrees. We have 90 degrees over here, so these two must add up to 90 degrees. But then if we look at this triangle right over here, we see that we have 90 degrees right over here already. Okay, and then we have angle theta. Okay, so what should this angle be? It has to be phi, right? Phi plus theta has to equal 90. So likewise, this triangle is good. And then if we look at the smallest triangle, if we have 90 degrees over here, and then we had phi here to begin with, then this angle has to be theta. Okay, theta plus phi gives me 90. Okay, so that's that. So if we use similar triangles to prove the Pythagorean theorem, what can we do? Well, let's just start off with this line segment H. Let's compare some ratios. So H is what? H is this line segment. It has a 90 degrees over here and theta degrees over here. Okay? But now, if we compare H to A, just this small triangle right over here, H to A. So A is obviously the hypotenuse of this small right triangle over here. So I know that if I'm comparing the small right triangle with the largest triangle, we have C over here, because C is the hypotenuse of this largest triangle. Okay, but now H has the angle theta and the angle 90 degrees. Okay, and then which line segment corresponds with the angle theta and angle 90 degrees? So we have angle 90 degrees and angle theta. It is B. Okay, so H to A, the ratio between H to A is the same as the ratio between B to C. Okay, so if A becomes C, if A was enlarged by some amount to become C, that means H is enlarged by that same factor, and that same factor when multiplied by B, multiplied by H will give you B. Okay, so that's what we have. And then what we can do is, I mean, this is true if and only if H is equal to AB divided by C. And of course, all of these A, B, C, H, M, N are positives. So yeah, we can go forward direction, we can go backward direction, no problem. It doesn't really matter for this case. Okay, but we have this equality right over here. Okay, now let us use some other similar triangles to help us figure other information. So if we have H to m. So let's compare h to m now. So h to m, if we're comparing h to m with the big triangle right over here, then h again is equal to b. H to m is equal to b over what? Okay, so m right here has the angle phi and the angle 90 degrees. And if you look at the large triangle, which line segment has angle phi and 90 degrees, well, it will be a. So like that over here. Yeah, so then this, what I mean is this line segment, the angles touching this line segment A, it is 90 degrees and phi. Okay, adjacent to it, or it's just you have a side and then angle beside it. So if we're looking at the largest triangle, then it will be line segment A. Okay, I'm not sure if that's the right terminology. Is it touching adjacent, right? So you have these angles right over here, adjacent, touching, corresponding to this line segment A. Okay, but here we have this, and then we also have h to n is equal to what? Okay, so now this is interesting. So h to n is 90 to theta, so on the largest it will be b again over here, right? Because this n is has 90 degrees in theta here, so on the largest triangle, 90 degrees in theta will be b. Okay, so b, and then h has what? H with respect to this triangle has a 90 degree and a phi. And on the largest triangle, the line segment would be A. Okay, has a 90 degrees and a phi. Okay, so with this information, let us isolate for m. So we have m is equal to, so what do we do here? So we can multiply both sides by a over b. So m is equal to ah over b. And so right here, n is equal to, so now I'll multiply both sides by b over a, b h over a. So right here we see that c is equal to m plus n. So then this implies that c, which is equal to m plus n, is equal to ah divided by b plus n is bh divided by a, which equals to, if we factor out the h, we get a divided by b plus b divided by a times h. But we know what h is. H is equal to, right over here, a b over c. Okay, so now this implies that if you multiply c on both sides, so we get c squared is equal to, so we have c is equal to this, okay? So multiplying c on both sides, we get c squared is equal to a divided by b plus b over a multiplied by ab. And of course, you can distribute the ab inside the brackets. And what do you get? You get a squared b over b plus ab squared over a, which equals to our well-known formula, c squared is equal to a squared plus b squared. Okay, so that is that, using similar triangles to prove the Pythagorean theorem. Okay, now for the, I should say, the inverse Pythagorean theorem, Pythagorean theorem. This isn't too well known, but I'll show you what it is. So let's just show how to derive it. well, essentially it is this. It's 1 over h squared is equal to 1 over a squared plus 1 over b squared. Okay, so this is the inverse Pythagorean theorem, dealing with this line segment h here. Okay, but let's just prove it. Okay, so let's start off with this antecedent. So we have h is equal to ab divided by c now. Okay, so this implies that if I reciprocate both sides and I square it, well, actually let me just square it first and then reciprocate. So h squared is equal to a squared b squared over c squared, and this implies that if I reciprocate both sides, I get 1 over h squared is equal to c squared divided by a squared b squared. This implies that, oh, actually no, not implies, this equals, okay, if you look at the numerator, we have c squared, right? But we kind of need to use this Pythagorean theorem to show that c squared is equal to a squared plus b squared, okay? And then divided by a squared b squared here in the denominator. So c squared is equal to a squared plus b squared. And then you can break up this fraction. It becomes a squared divided by a squared b squared plus b squared divided by a squared b squared. A squares cancel out here, b squares cancel out here, and then you get, so the order of addition doesn't matter. 1 over b squared plus 1 over a squared, same thing as 1 over a squared plus 1 over b squared. So then here we just have a chain of equal signs, so 1 over h squared is equal to 1 over a squared plus 1 over b squared, and that completes the proof for the inverse Pythagorean theorem.